Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Warahmatullahi wabarakatuh.
Very good morning, everyone. We are talking about simultaneous equation model. I hope next week we can join our offline class next Tuesday. Okay, one of assumptions in classical linear regression model, it is assumed that there is no correlations between independent variables and residuals. If there is a correlation, this means the estimated coefficient will be biased. So this is a very important assumptions in classical linear regression model. Okay, we continue here. Okay, in simultaneous equation model, we know now we call the variable. We have two kinds of variables: endogenous variables and exogenous variables. Okay. We have endogenous and exogenous variables. Okay, for example, here we have equation 18.11 and 18.12. You can see here y1 here is an independent variable, but at the same time y1 also is independent variable in the equation 18.12, and variable y2, it is also dependent variable in equation 18.12, but independent variable in equation 18.11. Now, why we call this y1 and y2 as endogenous variables? Because these variables exist in two equations. So this variable become endogenous variables. Okay, and now we have x1. X1 is only independent variables. Yeah, x1 in equation 18.11 and equation 18.12. So we call x1 as exogenous variables. Okay, so now you can differentiate two types of variables: endogenous variables and exogenous variables. Okay. Okay, here y1 and y2 are mutually dependent or endogenous variables, where variable x2 x1 is exogenous variables, and mu1, mu2 are the stochastic disturbance term. Variable y and y1 and y2 both stochastic, because these variables, okay, is available in equation 18.11 and also in 18.12. Okay, therefore, unless it can be shown that stochastic explanatory variables y2 in equation 18.11 is distributed independently of what? Mu1, and stochastic explanatory variable y1 in equation 18.12 is distributed independently of y. Mu2, application of classical OLS model to these equations will be inconsistent and also biased. Okay. Okay, for example, here we have demand. Okay, here we have demand for this one demand, this one supply. Okay, actually the simultaneous equation model, okay, for the simultaneous equation model, model. Okay. So could be equilibrium condition. Or identity. Okay, identity. For equilibrium, so we can get here, for example, Q demand is equal to Q supply. So here, okay, Q is the equilibrium conditions here. So we can apply to steady square. To this square. Okay. To steady square is also known as a simultaneous equation model. Okay, and we have also here identity here. Identity, for example, from the economy, okay, GDP. GDP consists of consumption from a household, investment from the private sector, government expenditure, export, and import. This is an identity condition. Another one is equilibrium condition. So, for example, if we have here consumption function is determined by income, for example, or another variable, interest rate, and investment is also function of income and interest rate. Okay, export is a function of exchange rate and foreign income. Import is determined by domestic income and exchange rate. So if we have, okay, here we assume G is an exogenous variable. Okay. So here we can use simultaneous equation model, or we can use two-state discrete model. Okay. Okay, here alphas and betas are the parameters. A priori, alpha is expected to be negative, downward sloping for demand curve, and beta 1 is expected to be positive because increase in price will be followed by increase in the supply of goods. Okay. Okay, now it is not too difficult to see that P and Q are jointly dependent variables. Okay, here P and Q is jointly dependent variable because if we equate Q demand is equal to Q supply, so we have the solution for this equation is P is function of parameters of this model. Okay, as the figures show that a shift in demand curve changes both prices and quantity demanded. Similarly, a change in mu, okay, for example, whether export, import, restriction, etc., will also shift the supply curve. Okay. Okay, if we solve this equation, okay, here we can see, for example, shifting in demand curve could be caused by income, other prices, expectation, taste, and etc. Okay, for the demand. For supply, could be technological change, okay, and other variables. Okay, in this one, the model of Keynesian model of income determinations, we have only two sectors here: household sectors and private sector. C is a consumption expenditure, Y is income, I is investment, S is saving, T is time, mu is stochastic distribution. Okay, the parameters beta 1 is known as marginal propensity to consume, this one, beta 1. Okay, beta 0 is autonomous consumptions. And beta 1 has a value from 0 to 1. Okay, this is an identity. This is identity. So if we insert C from the equation 18 to 3 to equation 18 to 4, we can get identity equilibrium. Okay. This one is which is determined by unemployment rate. Here, rate of prices changes. Change in prices, that's been inflation. Okay, inflation is also determined by expected wage. Yeah, we have change in the capital cost and also imported raw materials. Okay, since P entered into the wage equation and the wage variable enter into the price equation, two variables are jointly dependent. Therefore, these stochastic explanatory variables are expected to be correlated with the relevant stochastic disturbance terms. So this one, the valuation of important, one of the very important assumptions in classical linear regression model. Okay, here this is a good sector equilibrium. Here we have three sectors: household, private investment, and government expenditure. So we can insert first here. We have T here. YD, this means Y minus T, like equation 18 to 10 here. Okay, we insert this equation 18 to 10 into 18 to 7. And then we insert equation 18 to 8 into the T here, okay, to solve this equation. Okay, we have here, this is, we call it here reduced form. This one reduced form. Okay, reduced form means the equation that only consists explanatory and exogenous variables. Okay. Okay. In the simultaneous equation model, we cannot impose OLS directly to calculate beta null, beta 1, alpha null, alpha 1, and etc. So we have to solve first these equations, become this one. Okay, we call it a structural equation model. Okay, we have here reduced form here. This one reduced form. So we have alpha pi null is equal to this one, alpha 1, and pi 1 is equal to this one. Okay, equation 18 to 13 is the equation of IS, or good market equilibrium, It's give combinations of interest rate and level of income. Okay, we can draw this graph for the IS model like this. This figure 18.3. What would happen if we were to estimate the consumption function in equation 18.7 in solutions? Could we obtain unbiased or consistent estimate of beta 1, beta 2? Okay, so as a result is unlikely because consumptions depend on disposable income, which depend on the national income, and also determined by the interest rate and government expenditure. Okay, so we cannot use directly OLS to calculate this coefficient, satural coefficient of the equation. Okay, here we have example 18.5 is a ISLM model. Now here we have two sectors, good markets and also financial market. IS is a good market, LM is a financial market. Okay, here demand for money functions is supply. So we have equilibrium conditions. Demand is equal to supply. So we have reduced form for the money market or financial market is equation 18.18. Okay. ISLM curve show respectively that a whole array of interest rate is consistent with the goods market equilibrium. So here we have in here, okay, this is an interest rate, this is money supply. Okay, so here we have two exogenous variables. Okay, the exogenous variables here are the money supply and interest rate. Okay, this is a ISLM model. Okay, if we extend our model by using Klein's model, this is one Klein's model, it's more sophisticated model. We have consumptions here. Okay, we have also interest investment. Okay. Consumption is determined by P is a profit, W is a private wage bill, W prime is a government wage bill, PT minus 1 is lack of the profit. Okay, here we have this one is predetermined variable. We call it predetermined variable. Okay, predetermined variable is also exogenous variable. Investment is also determined by profit and previous profit and capital accumulation, so capital stock last period. Okay, so we have also this one is predetermined variable. Okay, all of the legs variables are predetermined variable. Okay, we have demand for labor equation here. It's determined by Y is income, T is tax, W prime is government wage bill, plus this one Y plus T minus W prime for the previous period, and T, okay, here beta 11 plus T. Okay, T is time. Okay, this one is identity. Identity. Okay, for the economics. Economy is in equilibrium conditions. Okay, here we have also identity here. Here also there is identity. Okay. Okay, the simultaneous equation bias, inconsistency of OLN estimator. As stated previous, the method of this square might not be applied to estimate a single equation model in a system simultaneous equation model. Okay, we cannot estimate directly. Okay. To show this, let us refer to the simple Keynesian model. Okay, of income determination and equation in example item 2. Suppose that we want to estimate the parameters of consumption functions, assuming that expected value of residual is 0, expected value of variance is sigma square. Covariance is 0. That means there is no correlation between these two residual. And also there is no correlation investment and residual. Okay, which are the assumptions of classical linear regression model? We first saw that yt and mu t in equation 18-3 are correlated, and then prove that beta 1 is inconsistent estimators of beta 1. So here, okay, we solve this equation. We get this one. This one is a reduced form. Okay. Now we have that expected value of mu t is equal to 0 in the assumptions of classical linear regression model. Okay. IT being exogenous or predetermined because it is fixed in advance as an expected value with this IT. Okay. Okay, and now we subtract from equation 18.32 from equation 18.31. So we get this one. Okay, here we know that the expected value of mu t is not equal to 0. Okay, and also variance here become variance is sigma square of 1 minus beta 1. Since variance is positive by assumptions, okay, because variance is that's been the square value, any negative value, if we take the square, so the negative becomes positive. Covariance between y and mu, given in equation 18.35, is bound to be different from 0. Okay, this one is not equal to 0. Okay, this one is not equal to 0. Okay. OLS estimator in this model is not consistent. That means the parameter of the equation become biased. Okay. So we cannot use OLS directly to estimate the parameters of the simultaneous equation model. So in the previous model, okay, here, expected value of beta 1 is beta 1. Okay, if it is not biased, okay, unbiased estimate. Okay, for example, here beta 1. So this means expected value of beta 1 hat is equal to beta 1. This means it is not unbiased. However, okay, if expected value of beta 1 hat, it is not equal to beta 1, that means it is biased. Okay. Okay, here. Okay. Here we have expected value of beta 1 is not equal to beta 1 because in here, in this part of equation 18.3x, the expected value of mu t is not equal to 0. Because it is not equal to 0, this means expected value of beta 1, not only beta 1, but plus something else. Okay, that means beta 1 become inconsistent. Okay, if beta 1 inconsistent, that means beta 1 become biased. Okay, this is for example, you can read this one, 18.4. Okay, identification problem. Okay, this is notation and definitions. Okay.